Okay, so random matrices, and the matrices which we consider are usually called Wishart random matrices. I mean, so that's the main ones we're interested in. I mean, there are many ensembles. I mean, random matrix means, of course, you have a matrix where you specify somehow the entries in a random way, and of course, how you specify this gives you different kind of ensembles. And I mean, the most famous one are maybe the Wigner or Gaussian random, the Wigner matrices, but those are symmetric matrices, and they were introduced by Wigner more in physics and so. But in our more statistical context, I mean, our matrices are more like the data matrices, and they are not a self-adjoint. They are not even a square. Okay, and those are Wishart matrices, and actually Wishart was a statistician who maybe for the first time really introduced random matrices, in particular in the context of statistical problems, so in the 1920s or so. Wigner was in 1950s or so later. Okay, but so I'm probably not going to talk about Wigner matrices, but really the ones which are more relevant in our context, which are called Wishart random matrices. Okay, so I mean, where do they show up in our setting? So I mean, we are looking on, let's say, random vectors, Gaussian random vectors. So that's our data. Our data, let's say, we model them by Gaussian random vectors. So our data, so this is a vector which, let's say, a p-dimensional vector which has a normal distribution, and it might have a covariance. So I mean, we don't necessarily assume that all the guys are independent and univariants, but could be more general. And very often the point is to, in statistical problems, to make from observations to get some information about this covariance here. Okay, so the sigma is the covariance matrix of my p components. So this is a p times p matrix. So this is the covariance matrix. And in the assignments we talked a little bit about the Gaussian random vectors. So that's what we should know. Okay, but now usually I mean, in statistical problems also, I mean, okay, usually you have some observations. Let's say you have n observations of your data. So we make n independent draws of a vector from this ensemble. And that's the information with which we can work, where we want to understand and maybe also infer something about the distribution or whatever. So consider, let's say, n independent draws from this distribution. So this means I have now n independent copies of this x. So I have vectors x1 up to xp, xn, I have n of them, and each of them is a p-dimensional data vector. And so they are independent, and each of them has a distribution, normal distribution with mean 0 and covariance sigma. Okay, and now I can put those p vectors, it's very convenient to put this into a matrix, because many things which I'm doing with those guys really are matrix operations. So it makes sense to put them into a matrix where I put them, let's say, as the columns in a matrix. So this capital X, I denote the matrix where the first column is the vector x1, then I have the vector x2, and so on, the vector xp. And so this is now a p times, up to xn, I have n of them. Okay, so n is a number which I have, and each of them is p-dimensional. So I have here n columns, and each of them has p rows. So this is a p times n matrix. I mean, that's somehow the data matrix. That's the data which we have as our observation. Okay, and then maybe one thing I might be interested in is, from a statistical point of view to get from this observations information about the sigma. I know somehow the distribution of the axis is a normal distribution with a sigma, but I don't know the sigma, and so I should estimate it somehow from what I have measured here, and then the canonical estimator for this is if I take x times x transpose. That's what I already denote by sigma hat. So this is 1 over n times x transpose, or maybe if I write it in terms of my observations, this is 1 over n, and here I mean x transpose. So if I multiply x transpose, it's just the other way around, and so you see I'm just summing over taking x1 transpose plus x2 transpose, and so on. So I'm not mixing my datas actually. I'm just taking the sum of k from 1 to n of xk transpose. Okay, I mean xk is a column vector, xk transpose is a row vector. So this is the inner. No, let me see, what is this? This is a matrix. Okay, this is not the inner product, but it's a matrix. Let me see. Xk is xk is a column vector. Xk transpose is a row vector. And if I multiply this, I mean I just multiply the I entry here with the j entry here. And this is a estimator for the expected value of this. So particularly if I'm doing this. Okay, so yeah. Okay, and of course, I mean, classical statistic tells me if n goes to infinity, if I can make arbitrary many observations, then this here will really converge to sigma. Okay, but the only problem in our modern times is that usually I cannot make infinitely many or a very, very large number of observations compared to the size of my data. I mean, p is the size of my data, the features in which I'm interested, and n is the number of observations, but now they are more of a comparable behavior. So I mean, what I get here, the sigma hat, contains some information about sigma, but it's not that it is equal to it. And in particular, we are interested in eigenvalues. And I mean, we had some histograms where we saw that you get here a shape where on first look it's very hard to see the underlying real sigma. But of course there is some relation, and if we understand this theoretically, of course we can make some inferences. Good, okay, but so that's the quantity we are interested in. Okay, so this guy here, so this is an estimator for sigma, and this is actually, the sigma hat is what is actually called a Wishart matrix. Sigma hat is called a Wishart matrix, and so this is a p times p matrix. For each n, it's a p times p matrix, and what we want to understand, in particular, of these matrices, or maybe also of the matrix X itself, is their spectral behavior. I mean, usually you're interested in the spectrum, in the eigenvalues. Many things you do in statistics, estimation, and so is you are trying to find maybe the eigenvalues. Maybe you think it's a good idea to only keep the large ones and throw away the smaller ones. That's the usual things you do, but you have to understand how this looks like. So we are interested in the spectral behavior or the spectral properties of this sigma hat. Okay, so I mean, we want to understand the eigenvalues of sigma hat, or maybe if I want to look on X, those are the singular values of X. So I take X times X transpose. The eigenvalues of this are the singular values. I mean, X itself is a rectangular matrix. It doesn't really have eigenvalues. eigenvalues itself. It only has singular values, but those are just the eigenvalues of X transpose. Good, so that's what we want to understand. And maybe, I mean, in the assignments, in the histograms, you already plotted some histograms for seeing some structure there. But maybe now, maybe we look on, maybe, if you have not on all of the eigenvalues, we look on this later, but now we just look on one of them, namely the largest one. That's, of course, also very important information. And of course, the largest one, the largest eigenvalue of this guy is, of course, the norm of the matrix. So essentially, we want to understand what is the norm, and in our probabilistic context, what is the typical behavior and deviations maybe of the norm of such random matrices. And we want to check whether our tools, which we had developed, allow us to deal with such questions, or maybe whether we have to go further. Okay, so we look on the largest eigenvalue, or singular value, largest eigenvalue, largest eigenvalue of sigma hat, or the singular value of X, or maybe just to say it another way, looking on the norm of a matrix. Okay, and so so what is our matrix? So our matrix is a P times N matrix. So we're looking on X now. So this is a data matrix. So it's a P times N matrix, or as a mapping, I mean as a matrix, it maps the n-dimensional space to the p-dimensional space. So it's a mapping from Rn to Rp. Okay, and we are looking on the norm of this mapping. Okay, so the norm of this. So what is the norm in general of a matrix? I mean, this is just looking how much can this matrix increase the length of vectors. What is the largest possible factor for increasing it? So essentially, you are taking the sup over all vectors, and I mean, you can restrict to the ones which have norm 1, because otherwise you just can rescale things. And then you're looking what is the length. Okay, so you start with a vector of length 1, and then you check how long is the vector after applying X, and this is the norm. Okay, if you don't have this restriction here, then you take the ratio of the norm afterwards with the norm before. Okay, so this is the general definition of the norm. And of course, because we are here in finite dimensions, this sup actually is a maximum. So it's achieved somewhere. So there is a vector such that this is really equal to the norm. So okay, so we can also write here the max. And what else do I want to say? And of course, I mean, the norm of X is the same as the norm of X transpose, and X transpose, this is a symmetric matrix. There, of course, the norm is the largest eigenvalue. So the norm is of course the largest eigenvalue of X transpose, which is the singular value of this guy here. Good. Anyhow, but that's what we are interested in. And so, what we are looking here is now actually a map. Or we have here our X, our matrix, and we are looking on this function here, which actually assigns to each matrix its norm, a value. So we have a function here. So what we have to understand is this value. I mean, it's a function which is defined on matrices, P times N matrices, but P times N matrices are of course just a vector of dimension P times N, just arranged in a matrix form. So I mean, if we want to go back to what we had before, where we had functions from vectors, then we should say, okay, our matrix is just a vector written in a matrix form. So I mean, of course, we can identify as linear space the matrices, a P times N matrix, with an R to the P times N. Okay, so this just means as a vector. And so what we have here is a mapping from this space here to this guy here. I mean, it's just saying, I mean, we are looking, in principle, we are looking on functions defined on vectors. Okay, but I mean, how can we build interesting functions on vectors? We can take norms, but okay, in the end, this is maybe not so interesting, but much more interesting is if actually we interpret our vector as a matrix, and then we can take eigenvalues. And eigenvalues are, of course, things we are interested in, but they are also non-linear things. I mean, they are not given by explicit formulas, or they're given, I mean, by something like this, but this is not really a very explicit formula with which we can work directly. Huh? So you see, I mean, okay, so this is really, we have here functions, and now we should check, does this fit into the frame of what we had before? Huh? For example, of course, this is a nonlinear function. Huh? So, so the hope is that it fits into our Gaussian concentration inequality, and for this we need Lipschitz. Huh? But this mapping, which assigns to a matrix its largest eigenvalue, this is a Lipschitz function. Huh? So why is this? So we have here a function from this space. So and thus it's a function like this, and considered as a function from here to here, as such, is a Lipschitz function. And of course, it will be interesting to see what is the Lipschitz constant. In particular, does it depend on the dimension or not? Huh? Okay, so what means Lipschitz? So I should take two matrices and compare what I get when I calculate their largest eigenvalues or their norms. I should compare this to the norm of their difference. Huh? So what should I do? I should compare the norm of x1 and the norm of x2. Those are guys in R. So I should take the distance in R, and I should see that I can compare this to the distance of those vectors, but now I mean in this space. Huh? And in this space, I have the L2 norm. Okay. But first of all, I mean, of course, I can compare the difference of the norms by the norm of the difference. That's just a general triangle inequality written the other way around. So this is true for all norms. So I can say this here is less than the norm of the difference. That's the triangle inequality, but just written the other way around. This is true for any norm. Okay, but I mean I want to compare this to the difference of my matrices, but not with the operator norm, which is maybe a canonical norm here in this space, but with the norm considered here as a Euclidean space. So I should compare it with the L2 norm, which is given by the sum of the squares of all components. And I mean that and this is actually the case. I mean that is what usually called the Frobenius norm or something of matrices. Huh? I mean, we have many norms on matrices, and one of them is really the one where you interpret your matrix just as a large vector, which means you're just taking the sum of the squares of all the entries. That's exactly the norm which you have here if you have it as a vector. And I mean, the operator norm is always smaller than this. So you really have this. Yeah, here I take the norm in R to the Pn. And I mean, this here is a general norm which is just compares the operator norm with this L2 norm or this Frobenius norm. I mean, there are different names depending on the community. There are sure norm. I mean, there are many. It's always confusing. Even if you put here indices, where if you put a 2 here, for some people this means the L2 norm, but for other people this means the operator norm with respect to L2. So it's always confusing which norm you actually mean. So maybe. Let me write it down here explicitly. So in this last step, we use the general estimate for the norm of a matrix. And with this I always mean the operator norm, as I have defined it there, for the norm of a matrix compared to its norm of a vector. So I mean, if I have my matrix, let's say xij, where I is running from 1 to p and j is running from 1 to n, so this is my p times n matrix, then okay, I have the operator norm of such a matrix, just defined in this general way. So then the norm of X, and this is less than this other norm, which often is called the Frobenius norm, but which is just the Euclidean norm of all those guys just considered as one big vector. Instead of writing it in a matrix form, you just put all the columns together, and then you just, what you then have as a vector, you just take the sum of the squares of each of them and the square root. So it's the sum over all components which you have, summing over all i's and all j's, and you just take the absolute value of the ij entries squared, sum all of them up, and this is the square of the norm, so you take the square root of this. And this is a norm. These Euclidean norms, they are quite easy. You can write them down very explicitly, and we could calculate concentration for them because they are very explicit. The problem with the operator norm is it's not so explicit. It's hard to deal with it. You have to work more indirectly. Okay, but anyhow, this here shows us that actually the operator norm is actually a Lipschitz function. And then we can just go into our Gaussian concentration. So if we now take the Gaussian distribution for our matrix, now if we take now the matrix where we say all the entries should be independent Gaussians, then if we just consider this as a large vector, this is just the Gaussian vector which we considered before. All the entries are just independent. Whether I arrange them in a large vector or in a matrix, of course, it's the same assumption. And of course, the Wishart matrices, now I'm in a situation where the sigma is the identity, where all the entries in my matrix are independent. That's what I can deal with here. Okay, so maybe this F here stands for Frobenius. Good, okay, but so the whole upshot of this is that actually the norm is a Lipschitz condition, and actually the Lipschitz function, and the constant here is 1. So in particular, it doesn't depend on P or N. No? That many things are Lipschitz is to be expected, but the question is more, does the constant which I have there, is it really small, or might it depend on P or N? No? So very often, if you go to higher dimensions, you might have an estimate for each dimension, but they might be put together just in an additive way, which means, of course, they are getting worse and worse if you go to higher dimensions. But here, actually, it's always 1 here, independent of P and N. So this is good. So the concentration also is not getting worse and worse with increasing dimension. Good, but so this means we have this Lipschitz condition, and then we can use our Gaussian concentration phenomena. Of course, convexity is here not so clear. Good, I'm not going to talk about convexity here, whether we can use Talleyrand or not. That might be a different question. So let's just use Gaussian, because there I just need Lipschitz for this. Yeah, okay, so let me then write down the theorem which we get from specializing our Gaussian concentration to this situation here. And now, of course, now I take, there the input was I had a Gaussian random vector where all the entries are independent. So this means in my setting with the Wishart matrices, it means the covariance matrix is equal to the identity. Okay, so if I take X, our matrix, and I consider it just as a vector which has mean 0, and all the covariance matrix of this vector is the identity, which just means all elements in my vector are independent, and each of them has a standard Gaussian distribution in the language of our matrices, or our Wishart matrices. This means that all the entries of my matrix are independent, and each of them has a standard Gaussian distribution, or This means if I take the covariance matrix of the vectors, this means I have the identity matrix, because that's saying exactly this. So this corresponds to the fact that the sigma is just the identity matrix there. Okay, so this means, I mean, yeah, for the Wishart matrices, maybe there I had some independence, namely I had independence between the rows, but within the row I had a Gaussian distribution where things might or might not be independent depending on sigma. Okay, I mean the sigma tells me what is the relation between the guys in a row. I mean different rows are always independent, and because I assume I make independent draws of the same data from the same data set. But within my column, okay, sigma governs the independence, and if sigma is the identity there, then this means all the entries in a column are also independent. Good. So okay, but so specifying our good old Gaussian concentration theorem for Lipschitz functions to this setting, so we have the following. So I suppose I look on a matrix now, xij, where I is running from 1 up to p, and j is running from 1 up to n. So if this is a standard Gaussian random matrix, let me call it like this. Also, I mean, standard is the most special situation. Standard Gaussian random matrix. So it's better to say what I really mean with this. So this means all the entries are independent. All xij are independent, and they are independently distributed, and of course we assume that distribution is standard Gauss. So the Gauss with mean 0 and variance 1. And each xij has a normal distribution with mean 0 and variance 1. Okay, and then I can apply my Gaussian concentration to this one Lipschitz function, the norm. Then I'm taking the norm of this matrix. Okay, and then our Gaussian concentration theorem tells us that the probability that the operator norm, I mean this is now a matrix and this is the operator norm of this matrix, if I compare this with the expected value of this operator norm, that this is bigger than alpha, this can be estimated against 2 times. 2 is just because I have here the absolute value. And then I get the exponential concentration, let's say, e to the minus alpha squared divided by 2. And here I would also have the L squared. L is the Lipschitz constant, but L is here 1. Okay, so you see I have an estimate like this. Okay, and this is, on one hand this is nice, but on the other hand it's maybe just as in this form it's not so useful, because actually we don't know what the expected value is. And so I mean usually we would say, okay, I mean we normalize things in such a way that we divide by something such that the expected value of the norm, let's say, is 1 or 2 or something like this. And then, of course, we get a dependency here, and then we really see concentration in the dimension. Okay, but of course, the main point is what was the expected value? And now we have here a kind of problem, because, at the moment, I mean, this theorem itself doesn't tell us what this is. This just tells us, concentration just tells us what is the probability of having deviations from the expected value. It doesn't tell us what the expected value is. In the case of the norm of a vector, in particular the norm of the square of a vector, we could calculate this very easily. I mean, the norm, the square of the norm of a vector goes like p, which means the norm should go like the square root of p. Okay, and maybe here we also expect maybe it should go like square root or something like this, but this is not clear because we don't have a formula, or maybe the only thing which we really have, which is as close as possible to a formula, is this here. But you see, this is not very explicit. I mean, I cannot just say I take the expectation here and then I know what it is. So this is not clear. And what I want to do now is to try to get some more information and really try to use this formula here. Because essentially, I mean, it tells us the operator norm is the sup over such quantities. And this quantity here is applying my matrix to a vector. And this is something which, in the end, is just another Gaussian variable. So, I mean, this here is the norm in the vector norm. Okay, so this is something which I can control much better. But I have to take the sup over many of those things, actually infinitely many. And so the question is, does this help me? Okay, and I want to show that we can use this formula to really get some more information, which gives us at least an idea what the expected value of the operator norm is. So we're not really going to calculate it exactly. This would be, for this we would need some other tools, but I want to show some general ideas that if you have a quantity which is given by the supremum over quantities for which maybe you are able to derive concentration inequalities where you also understand the expected value of those guys, then you might get something for this. But usually this is not, this is only up to some constants. Okay, but I want to give you the idea because this is also a quite general principle. Maybe it gives us an idea how this depends on P or N. Okay, so that's what I want to do in the following. But you should be aware, I mean, concentration inequalities are nice, but usually you have to complement them by the knowledge of what is the expected value, because the concentration inequalities only tell you how things concentrate around the expected value. And if you don't know the expected value, this is maybe not so useful. And usually, in interesting situations, maybe much work goes into calculating the expected value. Okay, so later, when we come back, not just looking on one eigenvalue, but on all eigenvalues of such Wishart matrices, then, I mean, we should get a distribution. And so deviation tells us that, usually the eigenvalue distribution is very close to the expected eigenvalue distribution. Okay, but then what you really have to do is calculate the expected eigenvalue distribution, and this is quite some work. Okay, I will talk a little bit about this later. Not today, but next lectures. But you should be sure that the task usually is split into two. You have to calculate the expected value, and maybe this is really, I mean, this is the thing about which in very high dimensions more or less everything concentrates. So that's really the quantity which you should know, because that's maybe the output of your algorithm. Okay, and then, so calculating this really gives you an understanding what this function does. And then this concentration is more of a theoretical nature, which tells you that indeed, in high dimensions, you're very close to this expected value, but it doesn't tell you more about the expected value. Okay. Yeah, good. Okay, but so now let me try to give you some idea how we could use this formula, or maybe let me even make it a bit even more accessible. So note, I can also write this, the operator norm. I can also, I mean the norm of my vector, I can also compare this with just taking inner products. So I prefer it to writing, and now I write really, instead of the sup, I write the max, because this is assumed somewhere. But now I'm looking on the inner product, so I have xv, I want the norm of xv, but I can also calculate this by taking inner products with other vectors and running over all possibilities. So I take here the maximum of vectors in R to the n, and then on this side I'm in R to the p. Okay, and again I assume that all of them have norm 1. So that's another possibility of writing this in a form which involves inner product. I mean, I still have here the norm, and inner products are even better than this. Good. Okay, so that's just a simple reformulation. I mean, this here is in any case smaller than this, and it is achieved because here you have a V where this is achieved, and then you can choose for the W. You can just choose a renormalized version of the XV. So this is quite trivial. Okay, and now we have written this guy here as a maximum over those quantities. And those quantities, I mean, what is this? This is my matrix here. So those are the xij's, and then they are multiplied with coefficients of my vectors. So what I have here actually is a linear combination of the entries of my matrix. Okay, and such a linear combination is just again a Gaussian vector. So what I have here is actually Gaussian vector, and so for each V and W I have concentration. Right? That's something for which I know concentration. And I also know it's concentration about, okay, and so the question is, if I have a quantity which is defined in terms of several conditions, whether concentration for each of those conditions gives me concentration for what I'm interested in. And I mean, we already had this idea, of course. I mean, if you want several conditions to be fulfilled, and I mean you can control each of them sufficiently good, then you can also control their intersection. So if you know each of them has probability close to 1, then altogether they also have probability close to 1, because you take essentially the union of them. But of course, I mean, if you have more of them, you're getting a little bit far away from 1. And now if you have infinitely many of them, okay, it might break down. No? So, I mean, each of them might have probability close to 1, but if you want to satisfy all of them, if it's infinitely many, this might be too much. Then the mistake, the errors which you have might become arbitrarily large. So the point is that if I have such a quantity, I mean, if I don't want to control it in infinitely many conditions, but I want to control it in finitely many conditions. So the question is whether I can go over here from having the max over all points on the unit spheres to something where I only control a finite number of them. And that's a general idea because I have here functions which are continuous. So this means if I control things on a finite number of points, and then I can also control it at points which are not so far away. So if I cover my unit sphere by points which have a small distance, then control on what happens there should give also me control on what happens everywhere. And that's this general idea that I should cover the space of my constraints, which is here given by the vectors in this unit spheres here, that I should cover this by a finite number of points, such that any point there has just a small distance to this. That's this idea of what is called usually an epsilon-net. So a number of points covering everything, covering the thing, such that any point has a distance at most epsilon from any of them. And then if I can control it there, then I can control it everywhere. That's a very general idea, which I want to make a bit precise here in this context. So, yeah. Okay, so, and maybe here I would have to cover the sphere, the surface of the balls, but maybe, maybe it's easier, not much easier, but maybe a bit easier to just cover the balls themselves. And so maybe I change this here by saying that, okay, it's enough to look on the situation. I can increase here by taking also the situation where the V and the W are inside the ball, because the maximum is achieved anyhow on the surface. Okay, so I just take here everything, and then I want now to cover. So I'm here in the ball of radius 1 in R to the n, and here I'm in a ball of radius 1 in R to the p, and I want to cover those balls by nets which have, let's say, a distance epsilon. So let n now be an epsilon-net, and epsilon is a distance which I will prescribe later, and actually it will be 1 over 4 or something like this. So it doesn't really have, it doesn't have to be a tiny one, but I mean, the epsilon in this context usually are numbers which don't have to go to 0 in some sense. Okay, so it's an epsilon-net for my ball. I take one here and I take one here. So let's say for the ball Bn, the n-dimensional, let me just recall, Bn are the vectors in R to the n which have norm less or equal to 1. In the Euclidean norm, we are here in R to the n with its 2 norm, the Euclidean norm. Okay, and so what do I mean with epsilon-net? So this means n consists itself of points in the ball. Okay, but they should have the nice property that for any arbitrary point in the ball, I can find at least one point from here which is closer than epsilon. So this means, if I take the epsilon balls about those points, they cover everything. So it's such that for any v in the ball, there exists at least one v prime from my epsilon-net, such that the v and the v prime are not further apart than epsilon. And this is then the idea that if I know properties on those v primes, they should also tell me corresponding properties on all the v's. So it should be enough to know the properties in which I'm interested on the points in the net. Good, okay, and of course the main point is to see, such nets exist. Of course I can't just take any point, but then the net would be as large as the ball itself. The point is, of course, to make the net as small as possible, in particular to see that it's enough to have a finite number of points, and also to understand maybe how many points do I need. Okay, and so the point here is that actually one can estimate, of course, the number of points in terms of epsilon. So I'm claiming, of course, we want this net to be as small as possible. And I'm claiming we can find a net where we can estimate the number of points in the net depending on epsilon as follows. So there exists an epsilon-net n such that the number of elements in this set can be estimated against 2 divided by epsilon plus 1 to the n. Okay, maybe we should see why this is the case, because this is an important ingredient that we really, we have here an exponential growth in the dimension. Of course, if you want to cover in one dimension the interval, of course, it's essentially like 1 over epsilon, how many. Okay, then if you have the disk, how many points do you need to cover this with an epsilon distance? It should grow exponentially in the dimension, but maybe let us check that this is really the case. And in order to see this, let us see how would we construct such a net. We want something which covers the whole thing, and we can do this by constructing inductively an epsilon-net. And let's say, this consists of points v1, v2, v3, and maybe a priori we don't know whether we can do it with a finite number. It should go with a finite number, but even this might not be so clear. We just create a sequence by choosing a new point such that this new point has distance bigger than epsilon over 2 from all the previous one. New point, let's say vk, such that the distance of vk minus all the VAs which I had already chosen before is bigger than epsilon over 2. So this should be true for all the previous ones, where I is running from 1 up to k minus 1. So this means that I'm starting by choosing just a point V1. Okay, and then I say, okay, I mean, this is, then I'm looking on the epsilon, not on epsilon ball, but epsilon over 2 ball, and then I say, okay, now I choose something new which is outside of this ball. So maybe I choose here, okay, no. So what I want is that, that I have a point such that this epsilon over 2 ball of this new point doesn't intersect the epsilon over 2 balls which I had before. So maybe here I should better say, so the ball about Vk of epsilon over 2 intersected is the ball about the previous ones, which its radius epsilon over 2 is empty. Okay, so I look on the epsilon over 2 balls. I try to put as many epsilon over 2 balls as possible there without intersecting. Okay, so I choose one here, then I choose one here, and then, okay, if there's a possibility, I put another one with radius epsilon over 2 and so on. Yeah, okay, but then at some point, it might be that I don't find any balls, any new point, so that I can put an epsilon over 2 ball about this. Okay, but this means, so this means at any point which I try as the next candidate, if I look on the epsilon over 2 ball of this, it has intersections with the ones which are already there. But this means, I mean, if this epsilon over 2 ball has an intersection with this epsilon over 2 ball, this means that this distance here can be at most epsilon. So this means if I'm not finding any new point, such that the epsilon over 2 ball of this new point doesn't intersect the epsilon over 2 balls, which I already have, this means that any point must have a distance at most epsilon from the points which I have already chosen. And I mean, that's what I really want for my net. Okay, good. Okay, so this means I'm choosing here a sequence such that the epsilon over 2 balls, I'm getting more and more, but they should not intersect. And there, I mean, there's only a finite number of possibilities for finding such balls because I can estimate the volume. Yeah, okay, so I construct those. And I mean, they are disjoint. And of course, all of them have to lie in a ball about 0, which has a radius 1 plus epsilon over 2. I mean, all those balls here of radius epsilon over 2, I mean, they are about points in a unit ball, so they might, the ball about epsilon over 2 might fall out the ball of radius 1, but it must be contained in a ball of radius 1 plus epsilon over 2. Okay, so we have, so all of those guys are disjoint, and the union over all of them, of the balls, of those balls here, they all lie inside the ball of about the point 0 of radius 1 plus epsilon over 2. I mean, somewhere is a 0, and I mean there's a big ball of radius 1 plus epsilon over 2. I mean, there's of course the ball of radius 1. All my points are inside this ball, and I mean I might have here a point like this, and then this epsilon over 2 ball might go a little bit outside, but not outside of this radius. So this means what I'm trying to find here are as many balls of radius epsilon over 2, which are all disjoint, but all of them together have to lie in this guy here. Okay, and I mean all those balls have a radius, I mean they are all balls of radius epsilon over 2, so they all have the same volume. Now I just take the volume. I mean the sum of their volumes must be less than the volume here. Okay, but I mean this means I get a bound how many I can have of them. Yeah. So this means in particular I can only find a finite number of them. So this means a number n. Okay, so So this means the construction stops after, let's say, n steps, because then I will not be able to find a new point which satisfies this condition, because after n steps, I mean I have n times, I have n balls which are disjoint, and each of them has a volume which is a ball of radius epsilon over 2 in dimension n. I mean, whether it's about 0 or some other point doesn't matter for the volume. And they are all inside the ball of radius 1 plus epsilon over 2. So I mean, n times their volume must be smaller than the volume of this big ball. So it must be smaller than the volume of Bn of 1 plus epsilon over 2. So I have constructed n of those small balls of radius epsilon over 2, which are all disjoint, and all of which are sitting inside this big ball here. Then n times their volume must be smaller than this. And this gives me an estimate for how big n can be. So an n must be smaller than the volume of the ball of radius 1 plus epsilon over 2 divided by the volume of the ball of radius epsilon over 2. Yeah, but now we know how the balls of a given radius in a fixed dimension behave. I mean, they essentially go like the radius to the power n, and then there are some constants, a gamma function or whatever, but I mean, I'm dividing here two volumes, so the constants go away. So the ratio is just this to the power n divided by this to the power n. So this is 1 plus epsilon divided by 2 to the power n divided by epsilon over 2 divided by n. Or if I divide this here, then I have here 1 divided by this is 2 over epsilon. 1 divided by this is 1. So I have this to the power n. Okay, so that's that's what I claimed here. Okay, so this is just making this precise. Or you just can believe it. I think exponential growth is something which is meaningful, but this here is a precise estimate. Where actually, I mean, if you want to cover something by balls, you should also try to pack smaller balls inside which don't overlap. I mean, I have here used a packing kind of argument. Instead of arguing directly with how do I find things which are closer than epsilon to anything, I've done it the other way. I'm trying to pack as many balls of radius epsilon over 2 inside the thing. And if I do this, this also gives me a solution to the other. Or I can compare those two things. So covering and packing is somehow connected. You can estimate one in terms of the other. Okay, so that's here this general thing. Okay, but so this tells me I have now I have an epsilon-net for any epsilon of my unit ball, and I can estimate the cardinality of this set in this exponential way. Yeah, now I can just do the same for the W, so I can cover R to the n, or the ball in n dimensions by a net, and I can cover the ball in p dimensions also by a net in the same way, and then I can try to see whether I can, the operator norm, I can also express it by something like this, where I'm just running over the net, which are then only finitely many conditions. So let me do this. So let us fix, I mean, epsilon is fixed in the following, and at some point I will choose it as 1 over 4. So maybe for now, maybe let me write still epsilon, but at some point it will be 1 over 4, because 1 over 4 you see then 1 plus epsilon over 2, if epsilon is 1 over, no, I mean this quantity here, 2 over epsilon, this is then 8 plus 1, so then the cardinality is 9 to the n at most of this net. Okay, so anyhow, so we choose, so I'm choosing an epsilon net, let me call it n, for Bn, and I'm choosing another epsilon-net for the same epsilon, let me call it M, for Bp, in n dimensions and in p dimensions. And then, of course, according to this, I know that in n I have at most 2 over epsilon plus 1 to the power n elements, and in m, by the same element, I have at most 2 divided by epsilon plus 1 to the m elements. M is here p. So good. Okay, and now let us see whether I can estimate the operator norm also by quantities like this over the net. And so for this, I mean, I know that I have this, and let me take the maximal V and W for which this here is maximized. And then see how I can estimate this by data from my nets. So let V in Bn and V in Bp be the maximizer for my norm, for my operator norm. So I know that this is the same as taking X on V inner product with W. Okay. And now I want to check whether I can express this in terms of my net. So I have an epsilon net. This means I can approximate V by something from its net, from the net in n dimensions, and W I can approximate something from the other net in M. So I know that there is something, an element, let me call it V twiddle, in n, in a net n, such that the distance between V and V twiddle is less than epsilon. And I also know that there is a W twiddle in M which approximates the W. So W minus W twiddle is less than epsilon. Yeah, and now I want to compare xv W. I want to compare this with the corresponding quantity when I replace V by V twiddle and W by W twiddle. And I want to see how big is the mistake which I have made. So this is, and for this, of course, I write the V here as V twiddle plus the difference between V and V twiddle. And the W I write as W twiddle and the difference between W and W twiddle. Okay. So I just have split it into two summands. But now, of course, this is bilinear, so I can multiply it out. So, of course, I get here the term V twiddle, W twiddle. I mean, that's the one to which I want to compare V twiddle and W twiddle. But, of course, there are mistakes. So, namely, what do I have? I have, of course, here X with the V twiddle. I also have the term going with this. So here I have W minus W twiddle. And then I also have this term going with the whole thing. And I mean the whole thing is just W, so I'm not splitting this one, but I just write it here as V minus, yeah, I have to V minus V twiddle. And here I have just a W. Okay, and those I can estimate. And of course they contain epsilon, because I have the difference. That's the point, that those are terms which contain the difference between the point and the corresponding point in the net. So I can estimate this against the norm of X times the norm of this times the norm of this. So it's less than the norm of X times the norm of V twiddle times the norm of V minus W minus W twiddle. And of course, norm of X is here. This element, this here is in the unit ball, so this is less than 1. But of course, this here is less than epsilon. And here in the same way, I also have this is less than the norm of X times the norm of this is 1, and this is epsilon. And so you see I get here, I mean this here is the norm, and you see on the other side I get the norm again, which might look as, okay, maybe not a very useful thing, but you see I have here coefficients which are less than 1, so I can bring this on the other side, and then I get an estimate for the norm in terms of this quantity here. So I mean, so maybe, so what I have here is the norm of x is less than this one here, x, we twiddle, w twiddle, plus, and then each of the two terms here is the norm of x times epsilon. But now you see I can bring this on the other side, then I have here the norm of x times 1 minus 2 epsilon, and then I just divide by the 1 minus 2 epsilon, and then I have a norm, the operator norm of x in terms of just quantities from the net. Also maybe let me write it. Yeah, let me write it here and then continue next time. So, I mean maybe a bit more space. Yeah, so I get here that the norm of x, let me write it as 1 minus 2 epsilon, so I'm bringing this on the other side, is less than the x we twiddle w twiddle. Okay, but now of course the v twiddle and the w twiddle depend on the vw from which I have started, which I don't know. So I mean, these are just elements from the net about which I don't know anything more. So I mean, I should, so this means there is something in the net which maximizes this. So I mean, what I really should say here, so that it's kind of uniform, I estimate this against the maximum where I'm running over my net. So I'm the maximum of v twiddle in the net and w twiddle in the other net of x v twiddle w twiddle. Okay, I mean in principle I have to control all the points in the net because I don't know which ones are appearing here. So there are some of them. So I mean I need all of them. Okay, but now and then of course, yeah, I can divide this on the other side. So the norm of x is now less than 1 over 1 minus 2 epsilon times this quantity here, the maximum of this. And now you see I have essentially replaced the original kind of definition of the operator norm by having a maximum over infinitely many guys by an estimate where I have the same kind of quantity but running over the finitely many elements in my net. Okay, and I mean it's on the expense of having here 1 over 1 minus 2 epsilon, and of course if epsilon is too big, this doesn't tell me anything. But I mean, if I now choose, for example, epsilon is equal to 1 over 4, then this here is a factor 2, and then I also know how big the nets are, and then I mean I can control each of those guys, and then I can also control the maximum over the finitely many, and this gives me something for the operator norm. Okay, and maybe next time I will put all this together, but this was here essentially the crucial step which shows how quantities which are given in this form by having to control infinitely many conditions can be reduced to controlling only a finite number of conditions. If you are in a situation where you have this epsilon-net, so you can approximate this infinite number of conditions by a finite number of conditions, so that still control for those guys gives you enough information for the control everywhere. Okay, and then it's just, I mean, then it's more or less just taking the concentration which we have for all those quantities and put them together. That's maybe more or less what we already should be able to do. But next time I will be a bit more precise on this. Okay, but let's stop here. here for today.